Welcome to Shanti-Peace for Mathematics. This video is based on a Taylor's theorem for functions of two variables. We already talked about the Taylor's theorem for functions of one variable in your previous study. In that, you required a function which is a real valued function defined over some interval to r. At x0, if you want to calculate a Taylor series for this one, then your function f should be n times differentiable function in the neighborhood of x0. Then you can able to write down f of x0 plus h is equal to f of x0 plus h into f dash of x0 plus h square upon 2 factorial into f double dash of x0 plus so on. The n minus 1th term will be n minus 1 factorial n minus 1th derivative of f at the point x0 plus rn, where this rn is called the remainder term, and the remainder term is nothing but the 1 upon n factorial nth derivative of f x0 plus theta h. For some theta belongs to 0, 1. This was the Taylor's theorem you have studied in your previous course. Here we are going to discuss about the Taylor's theorem for functions of two variables. So I required a function f which is defined over the domain D to R, where this D is a subset of R square, and I required a point which is in this domain D. Let us consider this n is the neighborhood of AB, which neighborhood is contained in this domain D. All partial order derivative of this f, that means I can write down all the partial order derivative of f are defined and continuous on n. So all the derivative of this partial order derivative of f is continuous as well as defined on this neighborhood. Let us consider this a plus h, b plus k belongs to D, with this h and k will be greater than 0. Then there exists some theta, it is in open interval 0, 1, such that we can write down as f of a plus h b plus k equal to f of ab plus del by del x h into del by del x plus k into del by del y f of ab plus 1 by 2 factorial h del by del x plus k del by del y square at f at the point AB, and so on, plus 1 upon n minus 1 factorial h del by del x plus k del by del y power n minus 1 f of AB plus the remainder term Rn is there, where this Rn is the remainder term that we can say it is 1 upon n factorial h del by del x plus k del by del y power n into f of a plus theta h b plus theta k. This is the Taylor's theorem for functions of two variables that we can state. So what is the requirement for the function? The functions, all the partial order derivative of this function are defined over this neighborhood as well as they are continuous on that neighborhood. Then we can able to write down f of a plus h b plus k in this form. Let us try to prove the statement this. So I am discussing here proof. So to prove this, we are going to discuss a Maclaurin series for functions of one variable. What is the Maclaurin series? In that this x0 is nothing but the 0. In this Taylor series, if the x0 is the 0, then that is known as a Maclaurin series. That is also you know. So I am going to use that Maclaurin series. Let us define this function g, which is defined over the closed interval 0, 1 to r as g of t is equal to f of a plus ht b plus kt, and this is defined for every t that is defined over the closed interval 0, 1. Now let us also say that x is equal to this a plus ht and y is equal to b plus kt. So now what is t equal to 0 will gives you? T equal to 0 will gives you x is equal to a and y equal to b. Therefore, g of 0 will gives you f of ab, and also g of t will gives you f of xy due to this. Now this f, by our assumption, what we have assumption for f is all partial order derivative of this f is exist and they are continuous. So therefore this f having all the partial derivatives are exist at the point xy and they are continuous in that neighborhood. Therefore this g is also n time differentiable function and its nth order derivatives, all the nth order derivatives exist. That means this g is satisfying all the conditions of Maclaurin theorem, and hence we can write down by Maclaurin series, therefore there exists theta belongs to open interval 0, 1 such that g of 1 equal to g of 0 plus g dash of 0 plus 1 upon 2 factorial g double dash of 0 up to so on. N minus 1 term will be 1 upon n minus 1 factorial nth derivative of g at the point 0 plus the remainder term Rn is there, where this Rn is nothing but the 1 upon n factorial nth derivative of g at point a plus theta h, but a is we have considered here 0, h is also we have considered as 1, so it is a which is 0 plus theta. So we'll have this. Now what is g of 1? You can just see this, that is the value of t is 1, so that's why it is x plus h. So g of 1 is nothing but the f of a plus h and b plus k that we got, and we have already concluded what is g of 0. G of 0 is f of ab that we can have. Now what is the situation? What is the g dash of 0? G dash of 0, that means dg by dt. dg by dt that we can have using the chain rule, that we can write down del f by del x into plus del f by del y into dy by dt. Because what is the situation? F and g are both the function, but f is your function which is a function of x and y, which we have considered, and x and y are the functions of t that we have taken. So your f is actually a function of t. So instead of this g, I may write down also f here. There is no problem with that. So that's why we have f here, we have f here, and we have by chain rule we can write this. Now what is dx by dt and dy by dt? So dx by dt according to this quantity, dx by dt is h and dy by dt is k. So therefore this quantity we can write down is df by dt is equal to h into del f by del x plus k into del f by del y, which I may write down as h del f by del, so del by del x plus k del by del y of f, and this is nothing but the dg by dt. If I want to write down, this is at the point 0, that means whatever the t equal to 0, this is nothing but at the point t equal to 0, and so at the point AB we'll have this one, so we have here AB. At the point AB we have, because at t equal to 0 we have your x will be a plus ht, and that t equal to 0 will have x is a, so we have this. Now what is del square f by del t square? Del square f by del t square is nothing but the derivative of this quantity again, h del by del x plus k del by del y of f of AB. We need to differentiate this one again, so by using the same chain rule we can write down this is as del by del x of h del by del x plus k del by del y at point f of AB into dx by dt plus del by del y into h del by del x plus k del by del y at point A of AB into dy by dt. Now we already know what is dx by dt and dy by dt. We'll substitute that value, so that's why it is h, and if I take this del by del x inside, then it will be h del square by del x square plus k del square by del x del y f of AB. This is applied to the f, so that's why it is f of AB, plus if I multiply, means if I operate this del by del y onto this expression, so that's del square by del y del x into h, and this for this one del by del t, if I multiply here, then it will be hk plus k square del square by del y square, and this is operate on f of AB. Now you just observe this is h square, this is hk del by del x del by del y, and since this f having all the partial derivatives are exist, so that's why this del, you know that fxy is same as fyx at the point AB, and hence this is nothing but we can write down as h square del square by del x square plus 2 times hk del square by del x del y plus k square del square by del y square, and which is applied on f of AB. This I can write down h del by del x plus k del by del y into del by del x plus k del by del y f of AB. This we can say, because you just multiply these two brackets, you will get to this quantity, and hence we can write down this is del by del x plus k del by del y square f of AB, and that is nothing but the d square f by dt square at point t equal to 0. Similarly, by mathematical induction, so by PMI, what we can actually write is nth derivative of this at point t equal to 0, we can write down h del by del x plus k del by del y power n f of AB. And if I use this expression into our previous expression that we got that we have here, g of 1 we have already calculated, that is f of a plus h b plus k, so that's why this is g of 1. G of 0, it is f of ab we have. G dash that we have calculated here at the point AB. G double dash we have calculated in the next page, that is here. And if I substitute all these values into the given expression, what we can get is this f of a plus h b plus k equal to f of ab plus h del by del x plus k del by del y at point f at the point AB plus 1 by 2 factorial h del by del x plus k del by del y square f at point AB up to so on. The n minus 1 term is 1 upon n minus 1 factorial h del by del x plus k del by del y power n minus 1 at the point f of AB plus Rn, where Rn is also we can write down as 1 upon n factorial h del by del x plus k del by del y power n at the point f at point a plus theta h b plus theta k. So finally we have the conclusion that if all the partial derivatives of f at the point AB, if they exist in the neighborhood of AB and they are continuous, then we can able to write down the Taylor series for this function. This expression, whole expression, can be also written in the form in this manner, that is f of a plus h b plus k is equal to f of AB plus h into fx at AB plus k into fy at AB plus 1 by 2 factorial h square fxx at AB plus 2 times hk fxy at AB plus k square fyy at AB, and so on. The previous expression that also can be written in that form that we have seen. This is the first remark I want to say here. Second remark that we need to say, by putting this value, that is a plus h if I substitute as x and b plus k if I substitute as y, then this expression is nothing but the f of xy, and due to this we can write down a is x minus h and b will be y minus k. So that's why this is, we can write down f of ab as it is plus h, we have this is the value of h, we have it is x minus k, so that's why it is x minus a fx at point AB plus y minus b due to this, it is fy at point AB plus x 1 upon 2 factorial, h square is there, so that's why it is x minus a square fxx plus 2 times x minus a y minus b fxy at point AB plus y square at fyy at point AB y minus b square, and so on. So this is the expression for the Taylor series we get for functions of two variables at the point AB. This is also known as the Taylor expansion of f of xy in powers of x minus a and y minus b. Okay, so in powers of x minus a and y minus b, this is the Taylor expansion of the function f of xy about the point AB. Next, the third remark we can write down, instead of A if I substitute 0 and B if I substitute 0, then it will give you a Maclaurin series. So the Maclaurin series of the function will be given by this f of AB, which is equal to f of 0, 0 plus x into fx at 0, 0 plus y into fy at 0, 0 plus 1 by 2 factorial x square f xx at point 0, 0 plus 2xy f xy at point 0, 0 plus y square at into fyy at point 0, 0 and so on. So that is the Maclaurin series of the function f of xy. So in this video lecture, we have discussed the proof of the Taylor's theorem and the different version of that Taylor series for functions of two variables. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye, sign off.